Hello, everyone. It is an honor for me to introduce to you Amit Singh, who works on macOS 10 technologies for Google. We met some time ago after both his team and my team independently ported Linux to the Intel Macs. So that was an interesting experience to meet him afterwards. Some time ago he invited me to Google to speak about hacking the Xbox, so I'm now very proud that he can be here in Berlin and speak about OS X hacking and the TPM. Also thank you to Anjol Lulaub who motivated him to come. So please welcome Amit.
Thank you. Good afternoon, and thank you very much. Thank you for inviting me, and thank you for coming here to this talk. This is a talk about the so-called DRM, or software protection, whatever you might want to call it, in the Intel version of macOS 10. It's also a talk about this little piece of hardware they call the TPM, the Trusted Platform Module. And in a way, I'd rather be using these things as excuses to take a little journey through the internals of macOS 10, kind of looking at how some parts of the system work so that we can understand what's exactly going on in the context of these things. Apple is a unique OS vendor. They're unique not because they have like a fanatic fan base or... Well, that's one reason. First of all, there are not many OS vendors left. And Apple has been dying for a long time. They just don't die. They always come back. But if you look at the history of Apple's operating systems, if you just look at the number of systems they have shipped and the number of systems they have tried to ship, it's like 3 dozen. Who has done that? Microsoft hasn't done that. Sun hasn't done that. No other OS vendor has done that. So I'm not saying that's a great thing, that you keep trying and you keep churning one thing after another and then it's forgotten. But at least they do that. So Apple gave the industry kind of a shock last year when they announced that they were giving up their long-standing relationship with the PowerPC and are going to start dating Intel. And well, it made lots of people unhappy. Well, it made me unhappy because I really like the big Endian. It's a big thing for me, and for a while I just couldn't reverse engineer anything because I'm like, what the hell is this? Why are all the bytes backwards? But at the same time, it made a lot of people happy. It made those people happy who wanted to use something that Apple made, who wanted to use OS X, but who didn't want to buy into Apple hardware. It also made those people happy who wanted to buy Apple hardware, but they wanted to run all kinds of operating systems on the machines. But it wasn't going to be so easy. I mean, if you expected that Apple's going to give all this to you on a platter, then you're mistaken. They're company. There were 2 important obstacles to begin with. One was that Apple chose, kind of expectedly, not to go with the BIOS. So they had a new firmware, which had been languishing in Intel's labs for a long time. Intel wanted people to use EFI a long, long time ago. And it almost died before Apple took it up, and now it's cool again. I actually talked to the person who's primarily the inventor of EFI, and talking to him a few years before and talking to him now, it's like he's like a new person. And so yes, since it doesn't have the BIOS, you at least have to do some work to do either of these 2 things, running another system on Apple hardware or running OS X on non-Apple hardware. The very first Intel Macs that were revealed to the public, I'm talking about the developer preview machines. It was found that they had these evil TPMs in them. And so did the first shipping Macs. So there was this whole mystery to the whole thing, that what is Apple doing with the TPMs and how does this whole picture fit in. And so I've done work on and off with TPMs. I used to work at IBM Research, and probably most of you know that IBM was a big player in at least the TCG specifications, and IBM were probably the first vendor to actually mass ship these things. But even then, it was kind of strange because they were shipping all the NetVista computers, all the laptops and the desktops with TPMs in them. Before that, there was some pre-version of the TPM, but nobody was using them for anything. And companies don't like that. They don't like to ship stuff that's not used and nobody knows what to do with it. And Microsoft is to be blamed for that, because Microsoft wanted to do their own thing with Palladium. And when people hear TPM, they equate it to Palladium, and they just don't like it. And this is kind of how they see it. This is how it is. So anyway, without taking sides in this yet, I mean, I don't think I'm going to take sides even at the end. So, but the combination of these factors kind of put a little cloud over the excitement of the people who wanted to use their new Macs for all kinds of stuff. Not so easy. Taking a moment to look at it from Apple's standpoint. So, what is Apple's most important asset? I mean, as an outsider, I think it's the users. Have you ever argued with an Apple user? I mean, I've come close to pulling my hair out at something that can be proven. It's like logical. It's logical in CS terms, and you tell them this is how it is, and they're saying, no, who cares? But anyway, so regardless of what Apple did with their new systems, DRM-wise, software protection-wise, licensing-wise, serial number-wise, whatever they did, they had to keep the users happy. I think that's really important for Apple, and they realize that. But the other thing is, if they like with PowerPC, Apple had a long run that it's like an esoteric platform. It's not. You can't just go out and buy a PowerPC machine. So Apple didn't really have to care about clone makers again. They didn't have to worry about people stealing. What are they going to run it on? But that would be a real problem now. So regardless of what Apple engineers think, Apple has to be able to sue people who, if you want to sell clones or something. And for that to happen, it has to be at least a little bit non-trivial to take their system and run it somewhere else. Because if you just pop the CD in and it works, then it's not going to hold water in a court of law. So they had to keep the lawyers happy. And engineers and lawyers don't really mix. I mean, with apologies to engineers and lawyers who might be present here. So Apple had a kind of a difficult problem on their hands. How much money and resources do they want to put in? So with that, let's make a context switch here. And in order to understand what comes afterwards, let's see if we can understand how virtual memory works in Mac OS X in like 5 minutes. So everybody knows that Mac OS X uses Mach. Everybody knows they don't use it as a microkernel. Everybody hopefully also knows that Mach was never used as a microkernel outside of a lab. But when people hear Mach, they say microkernel, which is really unfortunate. What's also interesting is that OS X VM subsystem is based on, it is the Mach VM subsystem, which is also the parent of the FreeBSD VM subsystem. And interestingly enough, when Sun was overhauling their VM subsystem at some point when going from Sun OS to Solaris or whatever, they independently came up with a VM subsystem that actually very close to Mach's VM subsystem. So in general, it seems like a good idea because all these smart people are coming up with pretty much the same design. So when you think of an OS X app, it's like, this is a stereotypical OS X app. It's kind of nice and candy-like, lots of interface elements. It's doing something very complicated in a very simple way. But in truth, when it's running as a bunch of threads. And actually, each of these is a mock thread. Now, I say mock thread because in all these mock threads, they live in a mock task. So why do I say mock thread? I say mock thread because it actually kind of looks like this. So the thing that eventually runs in the kernel is a mock thread. But depending on what you're programming, and you're using Cocoa or you're using Carbon or Java or something else, depending on that, you would deal with your own thread or process abstraction. But in user space, everything eventually boils down to a POSIX thread or a pthread, which has a one-to-one mapping with a mock thread in the kernel. If you have time left at the very end, please remind me. I want to show you a very interesting demo that kind of uses some of this thread stuff, but it's unrelated to the talk, so it's optional. So we have all these threads, and but what about processes? Because we know how close to Unix OS X is. Apple hypes that up a lot, and you can run the ps command and you can see process IDs, you can suspend processes, you can send them signals, you can do pretty much the same stuff you can do on a generic Unix system. So if we have all these tasks in thread, what is a process then? So that picture looks like this. What you see as a process and what you see as a process ID is essentially just some syntactic glue on top of a mock thread, because the Unix side has to be happy. The rest is kind of what I showed in the earlier slide, that you have pthread in user space, they have their own stacks, there's a one-to-one mapping, that you have mock thread in the kernel, they have their own kernel stack. All of them belong to this mock task. And the task is really this giant container which contains what actually concerns us here, the virtual memory of your program. So, okay, let's focus on the virtual memory aspect. So we'll just look at 32-bit processing because it's the same without making it more complex. So what is an address space? It's just a range of numbers from 0 to 4 gig. The name for address space in Mach is a VMAP. I think it's VMAP in many operating systems. There's also a physical map which contains information as to which of the virtual memory is currently physically resident. And the physical map is the only machine-dependent module. So, unless you're crazy or you've written some weird program, you're not going to be using all 4 gigs of memory. So, typically memory is sparsely populated, which means you have these blue regions that you allocated or were allocated on your behalf by the system. And a further subset of that would be resident. The rest may not be resident. So if the whole thing is a VMAP, then one of these blue things is a VMAP entry. And so VMAP entry it's just a contiguous range of addresses with the same properties. That's all it is. When I say properties, I mean the same sharing, the same inheritance, the same protection. And in fact, so you have a double linked list of all these VMAP entries, and in fact, if you go and change, some address range in the middle, you use mprotect or something else, then it's going to actually split it into 2 or 3 based on where you were. So okay, so far so good. Then we have something called a VM object. This is something that has information about that when you actually touch this memory, when you access it, where it's going to come from. We'll look at VM object in a second, but every VMAP entry has an association with one VM object. There could be sharing because nobody prevents you from mapping the same memory in multiple virtual addresses. So you could have a VM object that's shared between many things. Looking at a VM object further, it can be distilled to these 3 things. VM pages is just